Hello everybody and welcome to Unit 4, Matter and Energy. Today we'll be talking about thermochemistry. You guys will be able to demonstrate heat transfer between a system and its surroundings. You'll be able to differentiate between exothermic and endothermic reactions and then look at the heating and cooling curves in terms of the exothermic and endothermic reactions. So basically, when we talk about heat transfer, the most important thing to remember is that heat always transfers from an area of higher temperature to an area of lower temperature. So if you have a hot thing and a cold thing, heat will always transfer from the hotter thing to the colder thing. Okay? So let's say that's us during the summertime. Okay, the outside, the system, the surrounding around us, let's say we are the system and the surrounding, everything that we have around us, the atmosphere, it's very hot compared to our body because our body is comparatively cold compared to the surroundings. Now, as we just said, heat always transfers from the hotter object to the colder object because hotter object has a higher temperature, colder object has a lower temperature. So heat will transfer from the outside into our body. So heat will transfer from the surroundings to the system, which means the heat is entering in our system. Our body is absorbing that heat. So this type of situation, this type of a scenario is called an endothermic reaction because heat is entering into the system. So the quick way to remember that is that endo has an en, just like an en in enter. So endo means enter. Okay? So when we have a system that is absorbing the heat or the heat is entering into the system, then that's an endothermic reaction. Now, if on the flip side, let's say that's us during the winter time. Now, in the winter, the surroundings, everything around us, the atmosphere is very cold, and our body is comparatively hotter. So now, once again, heat always transfers from the hotter object to the colder object. So now heat is going to exit from our body. Heat is going to go out. Our body is going to release heat into the surroundings. Okay, and that's exactly why we feel cold because heat is our body is releasing all the heat that we have. So this type of situation is called an exothermic reaction because heat is exiting from the system. Okay, so whenever heat is being released or it's exiting the system, then that is an exothermic reaction. So in terms of chemistry, endothermic reactions are when we have a reaction that is absorbing heat. And those type of reactions normally happen when we are converting a solid into a liquid, which is a melting reaction. So let's say you have ice and you are trying to melt the ice into liquid water. That will require heat. So heat will be absorbed by the ice in order to melt into water. If you are trying to convert into a liquid into a gas, for example, if you are boiling the water to form steam, that type of reaction is evaporation, and that is also an endothermic reaction because heat will be absorbed by the liquid water to convert into water vapors or steam. And finally, if you want to convert the solid into a gas, that type of reaction is called sublimation, and it's very specific. For the most part, it only happens for carbon dioxide and iodine gas. And that type of reaction also requires heat to enter into the system. So heat is being absorbed. So this forward reaction, when we are trying to convert solid into a liquid, liquid into a gas, or solid into a gas, these reactions are endothermic because they absorb heat. So these reactions have a heating curve. Okay, and here's how this heating curve works. You guys will normally see this graph, and on this graph you see the temperature on the y-axis, and you see the time on the x-axis. So all that this graph is telling you is that what happens to these different products as the temperature increases with time. So let's say when the time is 0 and the temperature is also 0, we start with solid ice at point A. Now, as we increase the temperature and we move forward in time and we go from point A to point B, um, the ice is still, or the water is still in its solid phase. It's still ice. But as soon as we hit point B, as soon as we hit the temperature at point B, that specific temperature will be the melting point of ice, because that's the point, that's the temperature at which this solid ice will start melting into liquid. And then the ice will take its sweet time to melt into liquid water, and that will be this time between point B and point C. So that's the time when that phase change is happening. Solid ice is converting into liquid water. And during this time, there is no temperature change. The temperature is staying the same. We are at the melting point. Okay? Nothing's happening to the temperature. Only the phase is changing. Solid is converting into a liquid. Then once again, as soon as we hit point C, now all of that solid ice is converted into liquid. So from point C to point D, the temperature has started to increase again, and we are moving forward in time. So during this specific time between point C and D, water is still a liquid, but its temperature is increasing. Then as soon as we hit point D, that specific temperature will be the boiling point of water, because that is the temperature at which this liquid water will start converting into the water vapor, the gas form of water. So between point D and E, the water will take the liquid water will take its sweet time to convert into water vapors, into its gas form. But notice once again, nothing's happening to the temperature. The temperature is staying the same at this point. We are at the boiling point. Liquid water is converting into the water vapors between point D and E. Then by the time we reach point E, all of that liquid water has now successfully converted into the water vapors, or the gas phase of water. So once again, between point E to F, the water is now in its gas phase, and the temperature will continue to increase. So this is what this heating curve means, that we are going from a solid to a liquid to a gas. It's a forward reaction. That's why it's an endothermic reaction. So some of the things to keep in mind for a heating curve. Well, first of all, it definitely represents an endothermic reaction, because we are going from solid to a liquid to a gas, and we are constantly increasing the temperature. And all of these things are absorbing that heat in order for the reaction to take place. That's why it's endothermic. So the slopes, which were these tilted lines that you guys saw in that heating curve, they were representing the phases. And then the straight lines, which were lines like these, they were representing the phase changes. So remember, I said that during the phases, during those slopes or tilted lines, the temperature was increasing. There was a temperature change. But during the phase changes, when the solid ice was melting into liquid, or when the liquid was changing into the water vapors, there was no temperature change. Keep that in mind. Now, for those phases, for those slopes, because we were increasing the temperature constantly, remember temperature is the average kinetic energy. So because we were increasing the temperature, the kinetic energy was increasing and potential energy was staying the same. But during the phase changes, because nothing was happening to the temperature was constant, which means the kinetic energy was also constant. But the potential energy was increasing this time because all of that energy was being stored up now. So exothermic reactions, in terms of chemistry, is when we have a reaction that releases heat. And this happens in the backward type of reaction. So when you convert a gas into a liquid into a solid, gas into a solid. So if we try to convert a gas into a liquid, that's a condensation reaction. This is something that we saw in distillation. So remember, the water was boiling off first, it was evaporating, and then those water vapors were converting back into the liquid form. That thing is called condensation. So that when that happens, it releases heat. So that's an exothermic reaction. When we have a liquid that's converting into a solid, so when you have liquid water and you freeze that to make it solid ice, that's a freezing reaction, and that thing also releases heat. So that's an exothermic reaction again. And then when you have a gas and you're trying to convert that into solid, this reaction once again is not super common, um, but we still do that in lab sometimes. And that's called a deposition reaction, and it also releases heat. So that's an exothermic reaction. So exothermic reactions gives us the cooling curve, which is the exact opposite of what the heating curve looks like. So for a cooling curve, we start with a very high temperature. So remember, in heating curve, we started with 0 temperature, but in this case, at point A, we have a very high temperature. So at that point, we have water in its gas phase, which is water vapors. So as we go from point A to B, what we are doing is that we are decreasing the temperature. Okay, so heat is being released from the system. So we are decreasing the temperature, but as we go from point A to B, the water is still in its gas phase. As soon as we hit point B, that specific temperature will be the condensation point for water, and that is the temperature at which this gas or the water vapors will start condensing back into the liquid form. So between point B and C, we'll have the phase change. The temperature will stay constant at the condensation point, and all of the gas, all of the water vapors will condense back into liquid. By the time we reach point C, now we have all of the water vapors converted into liquid water. So now we have pure liquid water. Between point C and D, the temperature will continue to decrease. Heat will be released from the system, and water will stay in its liquid phase. As soon as we hit point D, that specific temperature will be the freezing point of water. And that will be the point when this liquid water will start freezing and convert into the solid form, which will be the ice. So between point D and E, liquid water will take its sweet time to convert into the solid form or the ice. And then by the time we reach point E, all of our liquid water has now converted into the solid form. It has frozen. So now we have solid ice. And then between point E to F, we will continue to decrease the temperature. But during these 2 points, the water will be in its solid phase, which will be the ice. So some of the things to keep in mind regarding the cooling curves is that, first of all, definitely they represent an exothermic reaction because heat is being released from the system. We are constantly decreasing the temperature in the cooling curve as we go from gas to liquid to solid. And once again, the slopes which were these tilted lines, they were representing the phases, and the straight lines were representing the phase changes. So during the phases, during those slopes, the temperature was decreasing. So there was a temperature change. But during the phase changes, during those straight lines, there was no temperature change. The temperature was staying constant. So during the phases, because the temperature was decreasing, the kinetic energy was also decreasing because once again, remember, kinetic energy is the average temperature is the average kinetic energy. So because the temperature was decreasing, kinetic energy was also decreasing and potential energy was remaining the same. But during the phase changes, the kinetic energy was remaining the same because temperature was the same, but the potential energy was decreasing now. So please review all of this information. Make sure you guys are well familiar with exothermic, endothermic heating and cooling curves. And I will see you guys with the next part of this chapter.